Assalamu alaikum. I would like to welcome you in our 10th meeting for today in M269 algorithms, data structures, and computability. So today we're going to talk about actually continue what we have started in our previous class, talking about graph algorithms. We have already explored different algorithms for actually representing graphs and for traversing also the graphs. And one of them, the one that we have used later in our in the end of our late class, which was the Dijkstra algorithm for traversing all the nodes in the graph. So today we are going to talk about a different one, which is part of the dynamic programming, which is called the Floyd-Warshall Algorithm. And that is for traversing and finding actually the shortest path between the given vertices in a given graph. And then actually we will talk about different paradigms in algorithms and strategies that includes brute force and greedy algorithm, divide and conquer, dynamic programming, and optimization programming. So we're going to give a brief description about each one of these paradigms. And then we will classify problems based on their types. We have different types actually of problems from their based on actually their hardness. So we have the P problems, general problems, the NP non-polynomial means stands for n-polynomial, non-polynomial algorithm, and NP hard and NP hard complete problems. And then we are going to talk later about the structure of the database, and specifically we will explore the SQL statements as part of the database management system. So starting with the Floyd-Warshall, and that is part of the dynamic programming. It is actually an algorithm that is designed to find the shortest path between every single pair of vertices in a graph. It is the shortest path actually between all pairs, not only two pairs. Now, the things that distinguish Floyd from a Dijkstra, it is actually can support negative weights. Yani what we have seen in the Dijkstra, that all the weights on the graph was a positive weight. Now we are going to deal with also negative weights over the edges, which connect two different vertices. And the runtime is actually for this algorithm is ON to the power 3, which is actually similar to the Dijkstra one. Even though Dijkstra for the path, for single path, let me draw it for you here. For Dijkstra, finding the shortest for every single vertex, it is going to take n square. But to find the shortest path for all the vertices, which is n, so it is n times, multiplied by n times, which is equal n to the power 3. So it is actually Dijkstra and Floyd-Warshall has the same complexity. So in Dijkstra, actually, we are finding the path between one node to all other nodes. But in Floyd, we are finding the shortest between all pairs of vertices. So that is the difference between. So we have two differences actually. One is that Dijkstra does not support negative edge weights, while Floyd do. Second, in Dijkstra, we find the shortest between one node with all others. But in Floyd, we find the shortest path between or among all pairs of vertices. This is just analysis of how we find the ON to the power 3. So this is a weighted graph, directed graph, where we have three different vertices, Tampa, Orlando, and Jacksonville. And these are actually three nodes in the graph, and these three vertices in the graph. And we have a weight which is represented over the edges, as you can see here. Now, we should actually draw the matrix, the adjacency matrix, every time we draw an adjacency matrix to represent the graph at the current state. So if you can see here, we don't have a direct path away from Orlando to Jacksonville. So in this case, it has a weight, and the weight is infinity. So if there is no a direct path between two nodes or two vertices in the graph, we can label them with infinite as indicating that there is no edge between the two connected vertices or unconnected vertices. Now, as an alternative, if I don't have a pathway from Orlando to Jacksonville, there is no direct way, I still can reach this place indirectly. So there is another weight because infinite is very huge number. So I can go to Tampa, and then from Tampa I can reach to Jacksonville. So the weight will be 1.5 plus 3.5, which is 5. So there is an Orlando, there is a path from this point to this point, but indirectly. So Tampa here is considered as an intermediate vertex. Intermediate vertex. So we want to start thinking about this using these concepts. Before we start, see how Floyd-Warshall actually find the shortest path among or between all pairs of nodes or vertices in the graph. Now, why do we call this kind of algorithms as dynamic programming? We call it dynamic because it's actually we are building. Every time we build a new block, we are just getting experience from old trial. Like for example, you will put one block here. Now, in order to go one step up, you have to use this block again, the same structure, and put it on top of it. Then, in order to go up again, you have to use your experience of building the previous step to build up a new one. So, your big problem is to build one stair, one big stair. But in order to build it properly, you need to divide the problem into smaller segments. And that's what happened here in this. So we solve this problem first, and this one, until we come up with the whole solution, which include the whole stairs. So the concept is to divide your problem into smaller segments, and even you still can actually divide the problem into sub problems. Yani this block also can be divided into another 2 sub problems. What is the difference between dynamic programming and what they call it, divide and conquer? In the divide and conquer, the 2 sub problems here and here must be independent. But here in dynamic programming, there might be some shares between the sub problems. And it's actually based on learning process. There's a learning process. That's why it's called dynamic. It's just changing. And we are going to see later how Floyd-Warshall is actually dynamic, because every time we build a new block, we actually extract the new information from the older one, and so on. It's a step by step. So what you can see here from this table is actually the adjacency matrix, which represent the graph. And of course, since I don't have a cycle from Tampa to Tampa, I don't have it. That's why I have 0 here. Also, I have 0 here. So I have zeros here because I don't have any cycle. So the diagonal line must always be 0 if you have no cycles or self-call. Since I don't have a pathway from Orlando to Jax, then I have here infinite, indicating there is no pathway or direct path from Jax to, from Orlando to Jacksonville. I want you also to understand how we read the values. We start from the row and then the column. So 1.7 is the row from Tampa to Orlando, not from Orlando to Tampa, because from Orlando to Tampa is 1.5. So we start from the rows first and then the column. Now, I would like to share the other screen with you to see how we are actually implementing and executing the Floyd-Warshall algorithm. Now we open, share a new screen. So I will consider giving you the following graph. Say I have 1, 2, 3, and 4. Let's assume I have a pathway from actually each one to the other. This way. And let us give some weights here. Say this one is 8. And this one is 3, 7, 2, some difficulties in writing. Wait, please. Okay, we have 7 here. We have 2 here. Okay, I redraw the graph again. And now this is a graph, and let's see how the Floyd actually works. First, we should start building our adjacency matrix, the original one, which describe the current weights of all vertices. So starting with this one, this is the original matrix. So we have 1. This is for 1, 2, 3. Let me draw it again. So this is the matrix, the original one, and let's see the distance between 1 to 1 is 0, and from 1 to 2, as you can see here from the diagram, from the graph, 1 to 2 is 7, uh, sorry, from 1 to 2 is 3, here, this one, and then there is no pathway from 1 to 3, so infinity. From 1 4 is 7, from 2 to 1 is 8, from 2 to 2 is 0, and from 2 to 3 is 2, from 2 to 4 is infinity because there is no path, from 3 to 1 it's 5, and from 3 to 2 it's infinity, then 3 to 3 is 0 because there is no cycle, from 3 to 4 is 1, and from 4 to 1 is 2, from 4 to 2 is infinity, and from 4 to 3 is infinity, and from 4 to 4 is 0. So this is the original actually matrix. This is the original matrix which is actually represent the weight of every single path between any given vertices. Now we have some issues here that this is not the optimal solution, where actually there are some pathways which are much shorter than what you can see in this diagram, on this adjacency matrix, especially the infinity. The infinity means there is no direct way, but we still have indirect way. So the first step to work on this is to build our next matrix, is to build a new matrix based on A0. So we will call it A1. A1. And it's supposed to be in this way. This is A1. We have 1, 2, 3, 4. These are the labels of the vertices. 2, 3, 4. What do I mean by A1? A1 means A is now considered as intermediate vertex. Intermediate vertex. So every time you move from one node to another node. So now 1 is intermediate vertex. Now let's go through the building A1, as 1 is the intermediate matrix. Now, since we are talking about 1 as a intermediate node, so there are no changes on any relation that is related, on any vertices or any weights related to 1. So all the columns and the rows related to 1 must be the same. So we have 0. Let me change the color for distinguishing the values. So from 1 we leave it the same, 0, 0, 3, 8, sorry, infinite, infinite, and 7. And the column stay the same, 8, 5, and 2. Nothing to do with it. Since there are no cycles, so the diagonal also will be kept the same, 0, 0, 0. Now what is left for us here? Let's see where are the updates. Which updates we should have. I will change the color. So we have one value here, and one value here, one value here, 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 and here. So we have 5 values that need to be updated. So we are updating or creating A of 1 based on A0. To start with this one, This one is actually 2 to 3. This is from vertex 2 to vertex 3. So I will say that this is actually based on the previous value, which is A0 equal A0. Sorry, let me put the vertices. So A0 of 2 to 3 equal, which is this one. This is A0 2 to 3 equal A0 2, which is the first one. Now we consider A1 as intermediate. So A to 1 as intermediate from 2 to 1 plus A0 1 to 3. You see what we did? So we put actually 1 as intermediate. We cannot go directly from 2 to 3. We don't want to go directly from 2 to 3. We will consider going from 2 to 1 and then from 1 to 3. So 1 here is intermediate. Okay, let's go back to the A0. So A2 to 3 equal what? Equal 2, right? 2 to 3 is equal to here. This is 2 to 3. So 2. Is it less than or greater than A2 to 1? A02 to 1 here. 2 to 1 is this one. 8. 8 plus A0 1 to 3. This is 1 to 3 infinite. So 2 is actually less than what? 8 plus infinite. So we will keep it the same. No changes. So here will be 2. Let's move to the second one. Next is this position, which is 2 to 4 here. Now A0 of 2 to 4 equal A0 of 2 to 1, as 1 is the intermediate, plus A0 of 1 to 4. So A0 2 to 4 is infinite. So infinite. Is it less than or greater than A0 to 1? This is to 1, which is 8. 8 plus A0 1 4. 1 4 7. So it's 15. Sorry. It is 15. So 15 is actually less than infinite. So infinite here will be replaced by 15. So we are going to continue with this process for every single position here we have with the same process. So the output of A1 will be as follows at the end of this cycle. So this is how A1 now works. We finished A1, the vertex 1 is done. Now we move to 2 as intermediate. So now we are going to consider another one, another matrix, which is A of 2. Now 2 is the intermediate. So now let's build the matrix again. A2 equal, this is for 1, 2, 3, 4, 1, 2, 3, 4. So the rows and columns related to number 2 will be fixed. So this is number 2, row number 2 will remain the same, which is 8, 0, 2, 15. As you can see, we are building a block. So we are building A2 from A1, nothing related to A0 anymore. 15, so these are fixed, and column number 2 is also fixed. So this is the 3, 0, 8, 8. Diagonal are also fixed, so I have here 0, and here 0. So what is left for us now? Left here, 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 and here. So we need to find first A, which is A from 1 to 3. So A from 1 to 3 can be found and specified as follows. Now A1 from 1 to 3, is it less than or greater than A 1, 1 to 2, because now 2 is intermediate, plus A1, 2 to 3. So let's go back to the A1. You can see that A1 to 3 is infinite. So infinite. And A1, and we need to know if it is less than or greater than. A1, 1 to 2 is 3, plus A1, 2 to 3 is 2. So 5 is actually less than infinite. So this actually infinite will be replaced by 5. And we keep doing this until we reach A4. So by A4, by reaching A4, we are finding actually the shortest path between all pairs of vertices. So again, there are two things. First, we learn how to actually find the shortest pathway in a nice way, in a good algorithm like this. Second is the concept of dynamic programming, where it is actually building blocks. We are building A1 from A0, building A2 from A1. So that's why it's called a dynamic process or dynamic programming. Programming, what we mean by here, programming is planning. It's called dynamic planning. So this is how actually the Floyd-Warshall actually work. Now let's go back to the slide. So by matching what I have explained so far, you can easily go through the pseudocode that you can see here and also match it with the example given to you. This is another exercise. Go through it by yourself and try to build. You see, for every single node, we should build its own matrices. So this is what I have already talked about in my earlier uh, presentation. So the process of dynamic programming starts with characterizing the structure of the optimal solution. In our case just now, the structure of the optimal solution is the structure where we have the shortest path among all pair of vertices, and we have to define a value for the optimal solution, actually recursively, uh, starting from either we can do it bottom up or top down. It's a recursive, and either we go up recursively or we go down recursively. And of course, if you want to use the top down, you can use caching, and if you use bottom up, we need to use tables. And these such actually the in details structures are beyond the scope of this course. And then after that, we construct the optimal solution from computed values. From the computed values, actually based on the top-down or bottom-up approach we are going to use. This is an example of a Fibonacci number. You know the Fibonacci series where the numbers is actually at position n is the summation of the two numbers before it. So 1 here is actually 1 plus 0. The next one you will find it 2. So because it's 1 plus 1 is 2. Next is 3 because 2 plus 1 is 3. Next is 5 because 3 plus 2 is 5, and so on. This is called Fibonacci series, and it can be calculated recursively using a top-down approach, as you can see this here. Now, moving to the paradigms of algorithms, the way that algorithms solve the problems actually can be classified using 5 paradigms. Brute force technique is the one that we have already discussed in our last 2 meetings, where we said this is actually exhaustive search, and every single a trial or every single option is going to be tested. But of course, this is a very slow process, and it's going to take a huge amount of time as it's going to try every single possible solution or candidate for a solution. The second part is the greedy algorithm, and here actually we are constructing a sequence of steps, but the problem is that we usually keen to select the best or the next optimal step based on what you see locally. I told you before we have usually two ways to find our optimal solution. Sometimes we can see the optimal solution locally within our vision, but there are sometimes better solution, but that is you cannot see it at that step. But in order to move to the better global solution, you need to take another step locally, which might not be the optimal at a given time. For example, if let's say I give you two options, you take a box or you take 1000 real. The optimal solution is to take 1000 real, but for you that is locally. But the box might lead you for another thing which is not seen. You cannot see the other solution that the box will provide you now, but there might be leading you. The box will lead you to a better global solution or optimal global solution. So if you choose the 1000 real, that is the optimal solution locally. This is what you can see now. But if you open the box, you might get a key, and the key will let you open a treasure box. So you couldn't see the treasure box now, but you took a step that lead you to the treasure box. So that is greedy, because greedy means I am just looking of what I have in my eyes now, what I can see now at this time. So I don't care what I will get in the future. So that's why they call it greedy. Divide and conquer is actually dividing the problem into smaller sub-problems and try to find a solution for every single sub-problem independently. And then these sub-problems going to be combined together to form the final solution. Something like similar to what we did in the quick search and the merge search. Dynamic problem, it's also actually similar to the divide and conquer, but the sub-problems are not independent. They are not independent. There might be some intersection between these sub-problems. And the process of solving the problem is actually based on the previous solutions. So sometimes you can call the previous solution in order to solve new problems. Optimization problems is actually how to find the best element from a given available alternatives. So here we are trying to find the best available solution. And usually the best here determined by a function called objective function. And we have different types, of course, of domains for these functions. We can talk about most of the optimization algorithms like genetic algorithms, ant colonies. We have the particle swarm algorithms. These are actually well-known uh, uh, algorithms that are work on optimization. So optimization here means we are trying to find the best solution among different solutions. Another type of the problem is actually um, or the problem that we are usually trying to work on solving them, they can be classified into different types and categories. Anyhow, these categories are explained briefly, very briefly here in this course, but there are so many other details which can be introduced in this domain. So we have 4 types of problems in mathematics. We call it types of problems. So we have the P problems, NP problems, non-polynomial type problems, and we have NP complete and NP hard problem. So how to distinguish between these types of problems based on how difficult is to find a solution for the given problem, or sometimes to verify the solution of the given problem. Let me give you a problem that might actually make the image clearer for you in this domain of problem. Is for P problems. The first type is if you are asking a question and the answer is actually can be either yes or no. It's only 2 options. And that is very easy, actually can be easily verified by your computer. So if you want to, for example, check if this number is odd or even, you can easily find the answer of this problem through your computer. And that is classified as simple problems under the category of polynomial time problem. The second one is the NP problem. And here, the question that have yes or no answer is actually can be easily verified, but are hard to solve. Yani it's easy to find and verify if the answer is correct or not correct. But to build the answer is hard. And hard means here it takes a long time for you to find the solution. So for example, the traveling salesman problem is actually has to find the shortest trip through some cities. And every time he must visit the city only once. So if you have 500 cities and you need to spend less than 3,000 miles on the road, right? So you have 500 cities and you need to spend 300 miles on the road to visit these 500 cities, and you visit each city only once. So if I show you the trip, how I visited the city, that take you to the 500 cities, the whole trip, the whole eternity, it's very easy to know if it is less than 3,000 miles or not. But it's very hard, even using computer, to build the best solution for 500 cities as eternity. So verifying the problem is easy because if you draw the lines for me, I know the distance between the cities. I know the distance. So verifying the problem is easy, but building the solution is hard. So that is the NB problem. NB complete problem are actually special kind of NB problems where if you can actually take NB problem and do some modification on it, it will look like NB complete problem. So you have another problem called the knapsack. Knapsack, if you have a bag, a knapsack is a bag, and you need to put some stuff on it, inside it. You have to put the most expensive one, and you have specific number of items that you can put in each knapsack. So finding a solution for this problem, if you can modify that problem and make it similar to the actually to the traveling salesman problem, then it's called NB complete problem. So we twisted the problem. The last one is the NB hard problem, and that is actually the worst type of problems in mathematics. And just to explain what do I mean by how hard it is, and it's going to take from you almost forever to know whether the answer is correct or not. So I will give you example which can make things clearer for you of how hard is the NB hard problems. Let's say I do remember that it's actually there's an example in one of the references I have read to describe the MBHA problem. They said actually, if let's say you have a dog, if I told you that if I own a dog, then it can speak fluent English. So we don't know whether he owns a dog or not, but we are sure that he doesn't own a talking dog. See, if somebody is saying for you, I own a dog, صح? I own a dog. If I own a dog, then it can speak fluent English. The first part cannot be verified. We don't know. We are not sure. But the second part, that the dog is speaking fluent English can be verified. We say that we are sure that he doesn't own a talking dog. But do you have any mathematical proofs that dogs cannot speak English? It's just because we never hear a dog speaking English. And that is the evidence. That is the only evidence we have. So we sure that he doesn't have a talking dog because we know that dogs are not speaking English. Can you prove that dogs are not speaking English? Mathematically, no. It's just based on our knowledge that we have never heard a dog speaking. Now, hundred of examinations on dog shows that dog lack of proper mouth shape and brain power. Means we already have biological experiment that shows that dog have no proper shape for their mouth, and they don't have the power of the brain to support their speaking. In fact, none of us would believe him if he said he owned a dog that spoke English. So, if a problem is NB hard, we have the right not to believe that it can be solved in polynomial time. So, we cannot verify, or we don't know whether the dog is speaking or can speak or not. It's just because we don't have any model that can prove that the dog can speak or cannot speak. It's just based on knowledge. So one day, if it happened that you hear a dog is talking, then you break the whole knowledge that everybody on earth knows. So till now, nobody can prove that dog can speak English. So the same concept is applied on the NP-hard problem. There is nobody can approve that you can find a solution for NP-hard problem, and it's going to take from you forever. So based on this, actually, we can say that NP-hard problems are the worst type of problems that we have, and finding a solution for such problems is almost impossible. Uh, Another type of problems, mathematical problems that are used in security, for example, let's say if I give you two numbers, if I say for you x equal, let's say, uh, 7 to the power 9, 7 to the power 9. So if you know the answer here, and if you know the total, I mean, if you know the total here, if you know the value of x, there is no way to find that the total was based on 7 to the power 9. There is no way to find back or retrieve back the answer. And that is called discrete log problem. Discrete log problem. Now, as we have completed the algorithms related to graph, we will move to different the structures actually based on SQL, uh, and that is structured query language for database management systems, usually used in database management system. So we have two languages used in SQL. We have the DDL, stands for the data definition language, and the DML, data manipulation language. So in DDL, we are using the language for building, creating new tables, deleting, modifying, updating attributes of the table. But the DML is used for query about tables and extracting information. So here is the structure of any given database management system, where we have the database, and it is a collection of data on a table, and in the middle we have a database manager for controlling actually the database, how to access the database, who has actually access, authorities to access the data, and who to make sure that we have integrity on the data. Like, for example, if there are two or multiple clients who are accessing the data at the same time, we make sure that the data are actually being accessed properly and updated properly, so there are no conflict between two people who are accessing the same data. And on the first or at the other end, we have the client who is actually writing some SQL queries, SQL statements for retrieving or storing data into the database. And the structure or the topology that is used, we have different actually topologies. That we have the database server, client server database, where the database is stored in a server, and that is related to SQL. So this is the server side, and we have the client side, where we have different clients using different APIs for actually accessing data. Like what you can see even here in the government, we have the same database of all everybody on Upshare, for example, and you can through Upshare you can contact or use this information using different other application, like for example Tawakkalna or Tabaud. Whenever you enter your ID, you can the system will recognize you. Why? Because every single application of those are actually accessing an API, which is authorized to access the database. Now, types in SQL, we have characters, two types of characters. We have char and varchar. Char is fixed length of 20, and varchar, it's a variable. You can write whatever you want. It's like 40, 30, whatever length. We have numbers. We have big int, small int, tiny int, real, float, money. So these are types of numbers. We have time and dates, date and date time, and actually these are the one that can be used for building tables actually. So we have, this is a table which has the name and the price and the category and the manufacturer. These are list of gadgets and photographs and household. Um, you can see that here the type is money, type is text, and this is the table name, and every single one is called the attribute name. The tuple is actually a record in a table, and the table is a set or a list of or set of tuples. So as you can see here, now let's go back. So this one is called a tuple, another tuple, another tuple. So the list of all tuples are called table or row, يعني tuples or rows. Here in this schema is we are mentioning the name of the table, and here the name of the attributes. We have 4 attributes. Sometimes you need a primary key which indicate that this field must not be repeated. It must be a unique value in this field. So you must underline the name here of the field. It might be the name, it might be the price, it might be the category or whatever. So underlining the name of the attribute means you are considering this attribute as a primary key. Here we can see an SQL query where this is a basic form. Select, use the keyword select and the name of the attribute, if one or two or many, from which table, where a condition. This is the structure of the basic structure of the SQL query. So select the name of the attributes from which table, where condition that need to be met. Like this one, select star means select everything from table called product where the category attribute equal gadgets. So this is what you will see. This one only, I will select everything means all the rows from the table called product category gadget. So I will see only these 2 rows. The output will be only these 2 rows. You see, these are the 2 rows selected. Here we select B name only, price and manufacturer from the table product where the price is greater than 100. So I will select only this field, price and manufacturer. So this one will not be included in the output, and the price must be more than 100. So only this one and this one will appear. So here is the target. So the single touch and multi-touch. And only 3 columns appear, category does not appear in the output. And of course, the where clause can be associated with either equal, less, or greater than, or less, or equal, and etc. Of course. So, or we can use the like. So, where is for setting up the condition, for matching the conditions in the numbers. Like for example here, the price, where the price greater than or less than. So I use the where here for numbers. But what if I want to do a comparison over a text? So I need to use the operator like. Like. So here is how I use it. Select star means everything from the table products where p name like percentage text percentage means go to the pname attribute to that column and find for me any value that has the text GIZMO. Let's see this example. This is select. I will choose another one. Okay, I think it's not mentioning here. So let's say, for example, here pname like gizmo. Let's go to the pname first. Here is the pname. This field. They are looking for gizmo. Does this mean only this one? No. This is right, gizmo. But also this part has gizmo, see? So it will include it. So it will return for you this one and this one, these two. Why? Because I write here percentage, percentage. Percentage, percentage means even if it is in the middle of the word, end of the word, beginning of the word, consider it. If you want to use only at the beginning of the word gizmo, then instead of writing percentage at the beginning, just write like this: gizmo percentage. This one will be restricted to gizmo at the beginning of the word, and so on. If you have, sometimes you will get some values that have duplication. So if you want to avoid duplication, use the keyword distinct. So if you write select distinct category from product, it will show you only gadget, photography, household. But if you did not use the word distinct, like what you did here, you will gadget, 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 gadgets repeated twice, while here it's repeated only one time. We can also order the result ascendingly or descendingly. So we use the order by keyword. So here we need the price, name, manufacturer, but the output must be ordered based on the price and B name. So we start the order based on the price. If we have two prices of the same value, then arrange or order them based on the P name. See here the P name. We order based on the P name, which is this field. Another one is the join, how to combine or connect two or more tables together. So we have the product table here and we have company table. We have two different tables. Now we need to join them together and make a connection with them. Based on what you can see here, there must be some common attributes between the two tables in order to connect them together. So what do we have? Here we have stock price and price. They are two different things, so we cannot combine them using the price. Country. Here we have country in the product. We don't have any country, so we cannot have the country. We have the category here, but we don't have any category here in the company, so we cannot consider the category. We still have the manufacturer and the P name. Based on what you can see here, Canon, Hitachi, Gizmowork, it is repeated in the manufacturer, but not the P name. So I can connect the two tables based on the C name with the manufacturer. Here is the connection. Because they are sharing the same attribute. So to join the two tables, you can write the following statement. So select P name price from product company, where that is the joining now. Manufacturer equals C name. See, this is what we did. Manufacturer equals C name. This is the connection. And the country, Japan, and the price is less than 200. See, we have multiple conditions. So now we did the connection. The output is Gizmo, Canon, Hitachi. But they want only from Japan. So they will take out this one from the output because only these two. And the price is less than 200. This is satisfying the condition. So the output is Canon, Hitachi. You see? Sorry. What I meant here is the price of the product. So the price is here less than 200. It's only this one. Single touch. Not the stock price, the price. Here, it was clear here, the price. Another example for finding the countries that manufacture the same gadget. So you can write the manufacturer equals C name and category equal gadget. And the result will be the same gadget from Gizmo Work. So this is from Gizmo Work and Gizmo Work is from USA. So thank you for your attendance.